Yes, students, from the connectivity from the last class. Now in the today's class, we need to discuss about the crystal structures. Okay, crystalline solids structures we can explain by using X-ray diffraction method. That X-ray diffraction method is also known as Bragg's equation. What is Bragg's equation? So equation we have to remember. So the Bragg's equation is equals to n lambda is equals to 2d sine theta. Okay, this equation is very important. How this n lambda is equals to 2d sine theta came, so that we have to explain now. Okay, dear students, so by using X-ray diffraction technique is useful to study of the crystal structures. Okay, and crystalline structures are crystals. Okay, that crystalline solids are having arranged in a planar structures, that plane 1, plane 2, like that they are arranged in a planar structures. So whenever this X-rays, if you are incident on the planes of the crystals, means just this is the two X-rays just I am introducing. Incident on this is the first plane, if n is equals to 1, and it is the second plane, n is equals to 2. Okay, dear students, now their wavelength is same, the lambda here, the wavelength is the same. When that incident X-rays are diffracted on the point A and point B, two X-rays, this A and B are called as lattice points. Okay, whenever if it is on incident on that point, then it will be diffracted and the rays will comes outside in this direction, and both that X-rays are traveling in the same direction, that is called constructive waves. Okay, constructive waves means both are traveling in a same direction, that is called constructive waves. And the incident angle here, it is theta, and it is also theta. And the second line, that incident angle here, it is theta, and it will be is equals to theta. And from this diagram we have to derive that how the n lambda is equals to 2d sine theta came, that we have to derive. So once you are observed from the diagram, okay, in the diagram if you observe that, for example, this is the first ray and it is the second ray, dear students. Now these are the parallel lines from the first ray and second ray. If you observe that this distance CB plus BD is the extra distance. The extra distance traveled by the second ray. The extra distance traveled by the second ray. The remaining distance is same. Okay. So in the above figure, the second X-rays traveled some extra distance, that is CB plus BD, than the first ray. And both the X-rays are present in the same direction. They are traveling in the same way. That is called as constructive interference or constructive waves. So when both are in the same phase, then the extra distance traveled by the second ray, that is CB plus BD, that is extra distance traveled by the second ray, is must should be equal to the an integral multiple of wavelength. Integral multiple of wavelength means n lambda. Integral multiple of a wavelength. So from the above diagram, CB plus BD is equals to n lambda. What is CB value and what is BD value, we have to derive, dear students. So from this triangle, this is the perpendicular triangle, and AB is the interplanar distance, its value is D. Interplanar distance between the planes first layer and second layer, that interplanar distance is D, as well as this also D. Okay, now that AB value is D, and from this first triangle ACB, the sine theta is equals to opposite by hypotenuse or diagonal. Opposite is BC or CB by hypotenuse means AB. AB value, we know that AB is the interplanar distance, its value is D. From this, CB is equals to AB sine theta is nothing but D sine theta. In the similarly, okay, dear students, similarly triangle ABD sine theta is equals to triangle ABD sine theta is equals to BD by AB, and AB value is equals to D. Therefore, BD is equals to D sine theta. Okay, just you have to substitute in the both D sine theta plus D sine theta is equals to 2D sine theta. D sine theta plus D sine theta is equals to n lambda. Okay, dear students. So the 2D sine theta is equals to n lambda is known as Bragg's equation. Is known as a Bragg's equation. Actually, this concept they are not given in your NCERT textbooks, but this formula is very important. What is Bragg's equation? The Bragg's equation has been derived by using X-rays. So the X-rays diffraction method is useful to study of the crystal structures or crystalline solids, and the crystalline solid structure is arranged in a planes, first plane, second plane, and third plane. So the X-rays, two X-rays with their wavelength is lambda is incident on the first and second planes, and they will be diffracted in that opposite directions. And the extra distance traveled by the second X-ray is equals to CB plus BD, and both that X-rays are in the same direction. That's why the extra distance traveled by second ray is an integral multiple of wavelength. Is an integral multiple of wavelength means n into lambda. CB plus BD value is equals to n lambda. Then CB value is 2D sine theta and BD value is also 2D sine theta. And 2D sine theta is equals to n lambda is known as Bragg's equation. Is known as a Bragg's equation. Okay, dear students. So let's see what is in the Bragg's equation that important terms. The important terms is n lambda is equals to, n lambda is equals to 2D sine theta is a Bragg's equation, where n is equals to order of reflection. N values may be 1, 2, 3, 4, 5 like that. And lambda is equals to wavelength of X-rays. D is equals to interplanar distance. Interplanar distance value they will give in question, and theta value they will give. Then we have to find out lambda. So theta is equals to angle of reflection. So the finally Bragg's equation, in that when the solids are arranged in a crystalline pattern and they are arranged in a planes, plane 1, plane 2, plane 3, by using X-ray diffraction technique we can find out the interplanar distance. That is called D is equals to called interplanar distance. So the Bragg's equation is n lambda is equals to 2D sine theta. Then the interplanar distance D is equals to n lambda by 2 sine theta. So if D we want to find out means D value we can find out, then the n value they will give and lambda value and angle of reflection also they will give in the question. Okay, D is called interplanar distance between the crystalline structures. So means solids are arranged in a planes, plane 1, plane 2, plane 3, like they are arranged in a systematic 3-dimensional manner. Okay, dear students. So the X-rays are useful to study of the crystal structures. So by using X-ray diffraction technique, Bragg has derived one equation is known as Bragg's equation, that is equals to n lambda is equals to 2D sine theta. N lambda is equals to 2D sine theta. Okay, dear students. Let's see the next important concept from the solid state chapter is what is a crystal lattice or space lattice. Crystal lattice or space lattice means is a three-dimensional arrangement. Three-dimensional arrangement of lattice points. Three-dimensional arrangement of lattice points is known as a crystal lattice or space lattice. What is lattice point? Lattice point is nothing but it is a point or place. It is a point or place at which point atoms or ions or molecules are present. That place, that exact point is known as lattice points. Like that, lattice points are arranged in a three-dimensional manner is known as a crystal lattice or space lattice. Crystal lattice or a space lattice. In crystal lattice or space lattice, one simplest repeating unit is known as unit cell. The simplest repeating unit is known as a unit cell. So here important parameters in crystal structures. One is what is lattice points. Second one is crystal lattice or space lattice, and what is unit cell. Okay, dear students, lattice point. Lattice point means it is a point, like that points will be present. These points at that point means it is a place or maybe point. At that point, what will be present, dear students? Atoms or molecules or ions are present. These points are called as lattice point. These lattice points, if you are arranged in a three-dimensional manner, these lattice points you have to arrange in a three-dimensional manner, like on three-dimensional manner. If you are observed that, then it is called as a three-dimensional manner, and these all are repeating points. These points are called as lattice points, and this 3D arrangement of lattice points, 3D arrangement of lattice points is known as a space lattice. 3D arrangement of lattice points is known as a space lattice or crystal lattice, and in which the repeating unit, the repeating unit means smallest repeating unit is known as unit cell. Okay, unit cell, it is called as a unit cell. Okay, dear students, and let's listen. What is unit cell? Unit cell means is a three-dimensional repeating smallest portion in the space lattice or crystal lattice is known as a unit cell. Just see the structure, dear students. These are the points. These points are repeatedly arranged in 3D manner. These lattice points. This lattice point is nothing but it is an atom or ion or molecules. Where they present, that place, that point is known as lattice points. These lattice points are arranged three-dimensionally in a systematic manner. That three-dimensional arrangement is known as three-dimensional arrangement. 3D arrangement. Arrangement of lattice points known as a space lattice. Space lattice or crystal lattice. Okay, in which the smallest repeating units, just see this red mark. This part is like repeating unit, like one more backside and front, like this smallest repeating unit is known as a unit cell. The smallest three-dimensional repeating unit is known as a unit cell in a space lattice is known as unit cell. Now we need to discuss about the types of unit cells. How many types of unit cells are present, and how many atoms, how many number of atoms or molecules or ions present in a unit cell. That is known as unit cell constant. That unit cell constant calculations also very, very important, dear students. Let's see that. We'll discuss those about types of unit cells. Types of unit cells. Okay, dear students. So the unit cells are divided into mainly two types. One is a primitive unit cell. The second one is centered unit cell. Okay, primitive unit cell or centered unit cell. So the unit cells are mainly divided into two types. One is primitive or simple unit cell. The second one is centered unit cell. Centered unit cell. Okay, what is a primitive unit cell? Primitive unit cell or simple unit cell means the unit cell in which constituent particles, means atoms or molecules or ions, presented only at the corner. For example, this is one simplest repeating unit cell. You have to imagine that this is a three-dimensional arrangement of lattice points, and the smallest portion, simplest repeating portion in a space lattice is known as a unit cell. The smallest portion, the atoms or molecules or ions presented only corners of the unit cell. These are the corners. This type of unit cells are called as a simple or primitive. Primitive unit cell. Okay, dear students, is known as a simple or primitive unit cell. Now, instead of the lattice points not only present at corners, and also present in the another parts of the unit cell, means maybe present at the center of the unit cell or face centers and edge centers, like the atoms are present. Those are called as centered unit cells. Those are called as a centered unit cell. Centered unit cell means in which the unit cell, the constant particles like atoms or ions or molecules present at the corners and some other positions of the unit cell, some other positions of the unit cell called as centered unit cells. So again, centered unit cells are divided into three types. One is body centered unit cell, the second one is face centered unit cell, and third one is end centered unit cell. The third one is a end centered unit cell. Okay, dear students, the first one, let's see, dear students, body centered unit cell. Body centered unit cell means the atoms are molecules or particles, ions present at corners as well as body center of the unit cell. Means these are the particles present at corners. First, their present corners is common for all centered unit cells. Other than the corners, the atoms may be present at body center, means in middle of the unit cell or center of the unit cell. That is called body center. It is called body center. This type of arrangement is known as BCC, body centered unit cells. Body centered unit cells. If the atoms or molecules or particles present at corners, now in the body centered unit cell, if you observe that how many lattice points are present, means they have 8 corners plus one body center. One body center, total 9 lattice points are present. Total 9 lattice points are present in body center unit cell. Whereas in simple cubic, how many lattice points are present? The number of lattice points. Number of lattice points is equal to 8 corners only. The atoms or particles present at corners only. That is equals to 8. 8 lattice points are present. In body center, total 9 lattice points are present. And face center, let's come to the point related to face center, FCC. Face centered unit cell means the atoms or molecules or ions present at corners as well as face center of the unit cell. Okay, now this is the simplest repeating unit, dear students, in which the atoms are present at corners as well as face centers. So in 3-dimensional repeating unit, in which how many faces are present, dear students? They contains 8 corners and 6 faces. 6 faces are present. So this is upside and down, and this is left, right, front, back, and one is above and below, front, back, and this back side and front side. Total 6 faces are present. So if you observe that 6 faces, for example, 1, this is 1, you have to imagine the 3-dimensional 1, this back 2, and 3, 4, 5, 6, like total 6 faces are present. So the lattice points, number of lattice points is equals to 8 corners plus 6 face centers. Total 14 lattice points are present. So in FCC unit cell, there are 14 lattice points are present, dear students. Now come to that. Next one is end centered unit cell. The third one is end centered unit cell. Let's see the diagrams also, dear students. End centered unit cell. The end centered unit cell means the atoms are present at corners as well as the lattice points are present at any 2 end centers of the faces, in opposite faces. Like it is called as end centered unit cell. Like this is one face, at opposite face the atoms are present. Like these are the 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. Total 8 corners are present and 2 end centers, 2 end face centers. So 8 corners plus 2 atoms are present at end face centers. End face centers. Total 8 plus 2 is equals to 10 lattice points are present in end face center or end center. In primitive, then 8 lattice points are present. And body center, there are total 8 corners are present and 1 body center. See, this is 1 body center atom. Total 9 lattice points are present. This points also very, very important, dear students. In compulsory 1 mark question or in objective exam also they are asking. For example, they will ask the question like this: how many number of lattice points are present in face centered unit cell? Means the answer is 14. How many lattice points are present in body centered unit cell? The answer is 9. How many lattice points are present in end center? Means 8 corners plus 2 opposite face centers, means total 10 lattice points are present. And in simple cubic unit cell or simple or primitive unit cell, how many number of lattice points are present? 8 are present. Okay, dear students. And in face center, total 14 lattice points are present. Okay, so these are the types of unit cells. So that unit cells, they are divided into based on the position of lattice points in the simplest repeating unit. So if the lattice points are only present at corners, those are called as a simple or primitive unit cell. Not only at the corners, they are also present in the another positions. Those are called as centered unit cells. Those are called as centered unit cells. Those centered unit cells are again divided into 3 types. One is body centered, face centered, and end centered unit cells. Okay, dear students. Now these unit cells has how many variable properties or measurable properties are present? Those are known as unit cell parameters. The measurable properties in a unit cell is known as a unit cell parameters. So if you are observed that in the unit cell parameters, there are one is length, edge lengths. There are 3 types of edges are present, and any 2 edges will attach with each other and making one angle that is known as edge angles. Edge angles are angles. Those are 3 types of angles are present: alpha, beta, and gamma. They are represented as alpha, beta, and gamma. And edge lengths are 3 types of edge lengths are present. They are represented by A, B, C. So total there are 6 parameters are present in every unit cell. In every unit cell, any unit cell you have to take, there are 6 parameters are present. One is 3 edges, and in between the any 2 edges they are making angle is 3 types of angles are present. Alpha, they are represented as alpha, beta, and gamma. So total 6 parameters are present. Okay, a unit cell is characterized by its dimensions along the 3 edges. The edges may or may not be mutually perpendicular, may be perpendicular or may not be perpendicular. If they are in perpendicular, average any 2 edges they are in perpendicular and making angle, that is called as axial angle, that is equals to 90 degrees will comes. If is not equal to perpendicular, then the angle may be more than 90 or less than 90 degrees will comes. So there are total 6 parameters are present: 3 edge lengths and 3 axial angles. Those 3 axial angles are represented by alpha, beta, and gamma. So these are known as unit cell parameters. Based on these 6 unit cell parameters, their unit cells, they are divided into 7 crystal systems. 7 crystal systems and 14 Gravius lattices are present. Okay, dear students, let's see those. See, just you have to imagine that this is the simplest repeating unit. Then the edge lengths, this is one edge length A, and this is the edge length B, and this is the edge length C. In between any 2 edges, their making angle is known as axial angles. So a unit cell is characterized by 6 parameters. Their A, B, C are the edge lengths, and alpha, beta, gamma are the axial angles. Okay, in between any 2 edges, for example, B and C edges, the making angle is alpha here. This angle is alpha, and remaining A and C, that making angle is beta. It is represented by beta, and another is gamma. It is gamma. Those are called as axial angles. So total 6 parameters are present. There are 3 edge lengths and 3 axial angles. Total 6 parameters are present, dear students. Okay, and these edge lengths A, B, and C may be equal or may not be equal. May be equal or may not be may not be equal. Okay, dear students. And same way, alpha, beta and gamma, they are maybe perpendicular or may not be perpendicular. May not be perpendicular. Okay, dear students, may not be perpendicular. Okay, that points you have to remember. Based on these numerical values, the relation between A, B and C as well as alpha, beta and gamma, the unit cells are crystalline units or crystalline solids. They are divided into 7 crystal systems. These 7 crystal systems, in that repeating units or 3-dimensional repeating units, there are 14 types of 3-dimensional repeating units are present, or 14 types of possibilities are present. 3-dimensional possibility is present. Those are called as Bravais lattices. So the crystal systems are 7, and the possible 3-dimensional repeating units are lattice point. The possible 3-dimensional lattice points or repeating units, how many are present, dear students? 14 are present. Those are known as Bravais lattices. Now we'll discuss about that 7 types of crystal systems, and every crystal system, how many Bravais lattices are present. Okay, then the total in the total 7 crystal systems, the including total 7, they are equal to 14 3-dimensional repeating units are present. That is called as 14 Bravais lattices are present. So here in this chapter, we have to remember the 7 types of crystal systems and the relation between their edge lengths and axial angles, and how many Bravais lattices are present in every crystal system, and examples of that particular crystal system. These 4 points we have to remember. We have to remember perfectly, and on basis of the tabular form, compulsory questions are asking in board examination in 1 mark question, or as well as NEET and JEE or CET examination, compulsory question they are asking regarding the crystal systems and Bravais lattices and relation between edge lengths as well as axial angles. Okay, dear students, we have to remember. There is no any way. So that points we must have to remember. Okay, let's see, dear students. Crystal systems. First, we'll discuss about that. What are the 7 types of crystal systems, and in every crystal system, how many Bravais lattices are present, and those Bravais lattices names or unit cell names we'll discuss. Okay, let's see, dear students, the first one, cubic crystal system. Cubic crystal system, there the possible repeating 3-dimensional repeating units are Bravais lattices. 3 are present. There's 3 names is simple, body center and face center. Cubic crystal system, there are 3 Bravais lattices are present. Those 3 Bravais lattices are simple cubic unit cell, body center cubic unit cell and face centered unit cell. The second one is tetragonal crystal system. There are 2 types of repeating units are present. That is simple and body center. One is simple, second one is a body center. The third one is orthorhombic. There are 4 types of Bravais lattices or 3-dimensional repeating units are present. What are those? Simple, body center, face center and end center. Already we know that what is simple unit cell, what is body center unit cell, what is face centered unit cell and end centered unit cells, how the particles or lattice points are arranged also we discussed. Now these 4 types of unit cells are present in orthorhombic crystal system. Orthorhombic crystal system. And fourth one is rhombohedral or trigonal crystal system. There are only 1 type of repeating unit is present, that is simple. And fifth one is hexagonal crystal system. There are only 1 type of Bravais lattices or repeating unit is present. It is known as a simple hexagonal lattice, simple hexagonal unit cell. And sixth one is monoclinic crystal system. There are 2 types of Bravais lattices are present. One is simple monoclinic unit cell. The second one is end-centered monoclinic unit cell. And the 7th one is triclinic crystal system. The triclinic crystal system contains only 1 type of unit cell is present, that is simple triclinic unit cell. Okay, simple. After that you have to add this name, triclinic unit cell. Monoclinic, there are 2 unit cells are present, simple monoclinic unit cell and end-centered monoclinic unit cell. Among these 7 types of crystal systems, main important one is cubic crystal system is very, very important. In the cubic crystal system, there are three types of unit cells are present. One is simple cubic unit cell and body centered unit cell and face centered unit cells. Face centered cubic unit cell, their packing efficiency, how much percentage of atoms are occupied in that particular unit cells in cubic crystal system. That packing efficiencies calculations also very important. Okay, dear students, now in that next tabular form we'll discuss about that crystal system, their edge lengths and axial angles, relations and examples we'll discuss. Okay, let's see, dear students, in that 7 types of crystal systems, the relation between their edge lengths as well as axial angles. Let's see the first one. In the cubic, cube means the edge lengths all are equal. A is equals to B is equals to C, and their edge lengths, the lengths should be arranged in the perpendicular manner. Then alpha is equals to beta is equals to gamma is equals to 90. For this cubic unit cell or cubic crystal system, there are 3 previous lattices are present. I said already: simple cubic, face centered, and body centered. Examples: NaCl, ZnS, copper, cesium chloride, and calcium fluoride, iron sulfide, lead, mercury, and silver. These examples also we need to remember, dear students. And the second one is tetragonal crystal system. There only any 2 edge lengths are equal. A is equals to B, not equal to C. And another, the axial angles are all are 90 degrees, means they are perpendicular with each other. Examples: white tin, tin oxide, titanium oxide, calcium sulfate, potassium ferrocyanide, and nickel sulfate. And the third one is orthorhombic crystal system. Their edge lengths all are not equal, and but axial angles are equal to 90 degrees, means they are all perpendicular with each other. And examples: rhombic sulfur, potassium nitrate, lead carbonate, barium sulfate, potassium sulfate, MgSO4 7H2, magnesium sulfate, heptahydrate. These are the examples for orthorhombic. And rhombohedral or trigonal crystal system. Their edge lengths are equal, but angles are not equal, means the edge lengths are not exactly perpendicular with each other. Alpha is equals to beta is equals to gamma, but they are not equal to 90 degrees. Not equal to 90 degrees means maybe more than 90 or less than 90, like that will be exist, dear students. Examples for trigonal crystal system: calcite, calcium carbonate is also known as a calcite, sodium nitrate, cinnabar, mercuric sulfide, and arsenic, antimony, bismuth, and potassium permanganate are the examples for trigonal crystal system. Okay, let's go for last remaining 3 crystal systems, their relations between the edge lengths and axial angles. Let's see, dear students. Fifth one is a hexagonal crystal system. In a hexagonal crystal system, if you observe that the edge lengths 2 are equal, A is equals to B, not equal to C, but angles alpha is equals to beta 90, means 2 edge lengths are perpendicular with each other, and the third one is the making angle gamma is equals to 120 degrees. Examples: graphite. So graphite is belongs to hexagonal crystal system. And zinc oxide and cadmium sulfide, ice means water, solid water means ice, and beryllium oxide, magnesium, zinc, and lead iodide are the examples for hexagonal crystal system. And another one is monoclinic. Monoclinic means A not equal to B, not equal to C, but alpha is equals to beta, alpha is equals to gamma, beta not equal to 90, means 2 are 90, one is not equal to 90, maybe more than 90 or less than 90 will comes. Examples: monoclinic sulfur and Na2SO4 10H2O and lead chromate PbCrO4. And triclinic crystal system: A not equal to B, not equal to C, alpha not equal to beta, not equal to gamma, not equal to 90. Examples: potassium dichromate and copper sulfate. Okay, so triclinic crystal system is very important. You once you observe that among these 7 types of crystal systems, cubic is more symmetric, more symmetric crystal system, and triclinic is